All right, so today we're going to continue discussion of logistic regression. Okay. Now, reminder: here is what happened last time when we talked about logistic regression. It is a supervised learning technique, meaning that there is a target variable, right? And moreover, it's a classification technique. Okay. That means that the target variable is categorical. More specifically, we're going to take a look at the cases when the responses, the categorical variable, which is target, has two categories. 0, which typically means no, or 1, which typically means yes. Okay? And let's use the same good old example that we considered when we discussed classification tree. Remember personal loan from the bank? So the bank wants to find out what type of customers of the bank are the primary candidates for accepting an unsolicited offer of a loan from the bank. In other words, bank sends envelopes or postcards to its customers hoping that they will call back and apply for the loan, right? Because that means income for the bank, essentially. Well, I believe your data is still sitting in the data folder. Take a look at your disk drive C folder data. There should be a file called bank CSV. Is it still there? It should be still there, right? We downloaded that, about a month ago or so, a month and a half ago. All right, so let's basically start making the model, right? So let's, first thing first is, of course, reading the data, right? So I'm going to say bank data, bank underscore data. How do we read it? Read CSV, right? Read.csv. And the file should be located drive C, folder data, file name bank.csv. Bam. And there it is. You should see only blue results, right? Now let's take a look at the structure, kind of to remind ourselves what does that look like, okay? What's inside. So I'm going to look at the structure of the bank underscore data, just like that, okay? So let's take a look. Well, first of all, 5,000 observations, true? So the file contains 5,000 customers. And about each customer, we know 12 different things, 12 columns, variables, right? Our target is going to be this one, personal loan. So the possible answers are yes and no. 1 means yes. This customer, when we mailed him or her, they applied to a loan, and 0 means there was no contact back, so nothing really, okay? All right, age, that is categorical, not categorical. What's the other one? If it's not categorical, it's what? Numerical, right? Numerical predictor, that's years, right? Years of experience may or may not be significant. We just have it on the file just in case, right? Also numerical predictor. Income level, that's in thousands of dollars. Family size, also numerical. Then we have average credit card balance, apparently also in terms of thousands of dollars. Education is categorical, right? And remember, we had 3 different levels of education: BS, bachelor, MS, master's, and doctorate. That means PhD, JD, MD, all these Ds, right? Okay. Then there is mortgage balance. So if the customer has a mortgage with the bank, which oftentimes happens, then what is the balance? 0 simply means that they may have a mortgage, it's just not with us, right? Okay, and if there is a balance, then it's here, for example, 155,000 is the remaining balance of the mortgage. Do they have securities account? Yes, no. Do they have CD account? Yes, no. Do they do online banking? Categorical predictor? Yes, no. And credit card? Do they use credit card issued by this bank? Yes or no? Okay, but that's what we know about each of the customers. Now, if I would ask you, what do you think is the strongest predictor whether the person will apply for the loan or not? What would you say? Like out of these things that we have here. I understand that personal loan is the target. That's what we're trying to forecast, right? Everything else is a predictor. Out of this listing, which variable do you think is the strongest one that influences the decision? Probably income, right? And it's not quite clear, quite honestly, we can speculate, right? Who are more likely to apply for the loan? People with high income or people with low income? Low, right? Because low means you don't have enough money, and therefore you're likely to get a loan from the bank, right? Well, on the other hand, it can be argued that if I make a lot of money, why people take loans? Well, typically it's mortgages, right? Or car loans, or sometimes education loans as well, right? These are basically big purchases. So if I have more income, I'm more likely to be able to pay it off, service the loan, right? So maybe higher income means I'm more inclined to apply. So argument can be made in both ways, right? So let's start just like what we did with linear regression. Remember when we looked at prices of Toyota Corolla, we said the only thing that influences, the strongest thing that influences the price is the mileage, and forget about everything else, right? We started with simple linear regression with only one predictor. Let's do the same thing. First model that we will build in logistic regression is going to be simple logistic regression. And I'm going to say that the only thing that matters for the loan application is person income. High, low, medium, whatever it is, that's what affects the decision more than anything else. So I'm going to be a simplistic guy. Alright, so here's the reminder, ladies and gents, how the regression will look like. Okay? In previous class, we discussed logistic function, right? Here, reminder, okay? This is what logistic function looks like. Y equals 1 divided by 1 plus e. Well, let me do it like that. exp, exponential of minus, let me call it z, not x, but z, okay? This is a logistic function, okay? And we even did the graph of the logistic function, right? So let me reproduce the graph again over here. So this is my z, horizontal variable. Here is my y, okay? Logistic function goes through the point 0, 5, right? If z equals to 0, not 6, but 0, then e to the power minus 0 is 1, and you have 1 divided by 1 plus 1, that's 0.5. This point right here, 0.5, right? As z goes to plus infinity, then e to the power minus infinity becomes a really small number, right? So 1 plus really small number is close to 1, and 1 divided by something really close to 1 is also 1. So therefore this is what the function looks like in the positive direction of z, okay? And same thing happens when you go to the negative direction, only it approaches 0. Whoops. So it looks like this, right? So this is the graph of the logistic function. Right? Remember? We did that in the previous class. And the idea basically is this. I can take full range of values of z, and the answers are going to be squeezed between 0 and 1, right? That's what the function does, right? It takes any value of z, and the answer is somewhere between 0 and 1, okay? And that's essentially what we want. We want for each observation to be classified as a 0 or as a 1, okay? Now, the only difference is this. Instead of z, I'm going to use a formula which looks a lot like linear regression. That's the reason why it's called logistic regression. It uses the logistic function, this one. But also it uses the expression which looks a lot like linear regression, what we discussed. So, in my very simple model, here's what I'm looking for, okay? I'm looking to calculate the probability of getting a loan. How likely the person is to get a loan, and that is going to be expression which is based on the logistic function, like this: 1 divided by 1 plus exp to the power minus And here comes the linear part, okay? So mx plus b, is that right? That's what you told me, right? Linear function in the US is mx plus b. Okay, so m, instead of x, I'm going to use what? What's my predictor? What am I using to predict the likelihood of getting a loan? Income, right? We discussed that. The strongest thing to predict is income. So m times income plus b. That's basically the formula, okay? That's what it is. So this portion looks like regression, right? What we just finished kind of a week ago or so. This portion does look like regression. But then I feed this regression into the logistic function, right? And it becomes logistic regression. And the answer, probability of 1, is going to be between 0 and 1, right? At the end. So that's the idea, basically, how the logistic regression works. Okay? Well, ladies and gents, let me show you how it's done in R. Okay? Or in quiet words of Arnold Schwarzenegger, enough talk. Okay? Let's do some action. All right. So let's go ahead and do the simple logistic regression. Okay? All right. So I'm going to put a comment. Seems like there's been a long time since I commented out any of the code, right? So build. We don't say build anymore, right? What do we use? Which word do we use? Train. Train the logistic regression model. Okay. All right. So I'm going to call it personal loan. You know how I like to give my models and variables really long descriptive names, right? Personal loan, logistic, let's call it simple. Logistic regression. Okay, personal loan, simple logistic regression. How about that? Turns out that I don't even need to call any libraries. It's built into the R. Okay, and it's called GLM. LM stands for what? Linear model. G stands for generalized. Okay. So linear model means I have this linear function mx plus b, right? But then I feed that thing into the transformation function. In our case, it's going to be logistic function, and then that will be my model, right? So this logistic function is what makes this so-called generalized linear model. Okay. So at the core, I have linear function, and then it becomes transformed into something else. That's why we have G. G as in generalized linear model. Okay, so here I need, just like before, okay, I need to say what's my target and what is my predictor or predictors, right? My target is personal underscore loan, right? That's what I'm trying to predict, zeros and ones, tilde. And my predictor for now I have only one, right? And that would be income. So I'm going to say out of all variables, column, which is the same thing, right? Use only target, personal loan, and income as a predictor. Sorry? Personal loan, yep. So thank you. Personal loan. Can you guess what I need also to specify after that? Data. Which data to use, right? Data equals, well, my bank data, right? For now, I'm not breaking it into the, what's it called? Training and validation sets, right? We're going to do it next week, actually. Okay? When we're going to train a much bigger problem model with more predictors, that's when we're going to split it into training and validation set and do the whole 9 yards again, okay, with confusion matrix, okay? For now, I'm using the entire set as a training set. Bank data. And the last thing that I have to actually specify is this one. So, it's going to be a little weird, okay? I have to say which transformation function to use for the generalized linear model. That transformation function is logistic function, right? This is how it's done. You have to say family, okay? Family Oops, family equals. So I guess what I'm saying is this. For the next exam, that should be on your cheat sheet with formulas in R, right? With functions in R, okay? So that when we trained classification tree, remember in function R part, we used what? We said method, right? Method equals class, right? When we do the prediction, we said type of prediction equals class, or type of prediction equals ANOVA, right? This time around, it's a new name of the parameter. It's called family. This is just something that you have to either memorize or write down on cheat sheet when it comes to the exam, okay? So family equals, quote unquote, binomial. Binomial. That's how we tell GLM function that you have to use logistic regression, okay? Family equals binomial, and that's it pretty much. You run it, you don't see any red bad stuff, right? It's all good. Okay, excellent. Everybody okay? Wonderful. So let's take a look. What is our model at the end of the day, right? So summary, just like what I did for my linear regression, all I have to do is say summary, and this really long name, personal loan simple linear logistic regression, right there, okay? Bam. And then I run it. And the summary, as you can see, looks a lot like what we saw for the linear model, right? Same thing really. It has table with coefficients. We have intercept. We have income, slope, right? Estimates, that's where basically the model really is contained, okay? And at the end, you can see that I have probability greater than z. What's that for? The last column. What do I find there? That's p-values, right? So essentially, all that we discussed last couple of weeks about linear regression applies here, okay? I can do the same exact test to see which variables are useful, which variables are useless, okay? Same exact thing as what we did for the linear regression. That's the beauty of it, okay? We'll learn linear regression, now we'll translate directly into the logistic regression. So same exact principle, okay? All right. So now let's go ahead and write down the regression equation, okay? So I'm going to do it right here, actually. I don't want to switch between one node and R. Just go for it. So here's what my logistic regression looks like, okay? So I'm going to say, hear ye, right? So my logistic regression formula. Okay? This is what it looks like. I'm predicting probability of 1, right? Probability that a customer will agree to a loan, right? E of 1, between 0 and 1, okay? Equals, it's 1 divided by big expression, right? And it's 1 plus exp, exponential of what? Well, minus, and then my linear regression portion, right? So I'm going to put a bunch of spaces. I don't know if it helps or not. Okay, so slope. Where is my slope? My slope is right here. I'm just going to take that. I'm going to keep for now just four decimals. Okay. So here is my slope times income, right? Income plus the intercept, and my intercept is right here. It's actually negative, right? So it's not really a plus, it's a minus. So right here I have minus. Yep. So this is what my function looks like. Logistic regression function. Okay? It's a little ugly, right? Well, let me actually write that out. Okay? So over here, because it doesn't look that pretty over here. So my logistic regression, logistic function looks like this. P of 1 equals to 1 divided by 1 plus exp minus point, oh crap, I can't remember, come on, 0.0371 times income minus 0.0371 times income, and minus, right, if I remember correctly, because it's plus, but it was minus sign, 6.1273. Okay. 6.1273. And that closes the bracket around the regression portion, and that closes the bracket around the exponential portion. Okay? So that's my model essentially. How do you like them apples? Any questions? Is that confusing? Let me ask you this. Or not so much? Were you able to follow? Okay, nay? Okay, okay. Well, let's take a look at some examples, right? So this is my model, and after that I can predict pretty much anything, right? Okay, so I guess you may remember from the beginning of the semester that I can use R as just big fat calculator. Okay, so in other words, I can actually compute the expression. Okay, so let's try that. Say, for example, there is a person with $60,000 income. Are they likely to get a loan from the bank when the bank proposes, or not? How do we know? Well, we use the formula, right? So let's go ahead and predict. So let me put a comment here. Predict likelihood of a loan. I don't know how to agreeing of a loan application. Let's just put application for a person with income equal 60, and that's thousands of dollars, right? Because all numbers are in thousands of dollars in our sample. Okay, so here's what I'm going to do. I'm going to basically tell R to compute quite literally the formula for me. So 1 divided by 1 plus, can you guess how do we create exponentiation? EXP, right? Just like the same in Excel, right? EXP of the expression, and that would be minus, right? And then I open close another set of parentheses. 0.0371, that's the slope, times what? Times 60 minus 6.1273, right? So I literally took this formula and I plugged in income equals 60. That's all, right? That's what it is. And let's see if I can run it. Yes, I can indeed. Okay. So now I calculated the probability for that person that they will get a loan from the bank, probability of 1, right, equals to 0.0198. Is that a huge probability? 0.0198. 2%. No, it's not, right? So how do we classify them? Are they a 1 or are they a 0? 0. What do we use to classify observations? 0.5, not 0.5. 0.05 we're using to test hypothesis, right? Normally. Remember what we did for classification tree at the beginning of the semester. We said default cut-off proportion is 0.5, right? Whatever is higher than 0.5, that's how we classify that, right? So now probability of 1, probability of getting a loan, is 0.01. So therefore, according to my cutoff, this is below 0.5. So that person I will classify as a 0. So in other words, anything below 0.5 is a 0. Anything above 0.5 is a 1. Simple as that. 0.5 is again my default cutoff probability. Just the same as what we had before for classification tree. You see that? How we're using our knowledge from the previous models for right now? Yeah. But this is default. Is there any rule anywhere that says it cannot be changed? Not really. And later on, next week probably, we're going to take a look at what happens if I start messing with this 0.5. What if, for example, I take not 0.5 but 0.3? Anything below 0.3 I classify as a 0. anything above 0.3 I classify as the 1. Can I do that? Sure, I can do whatever I want, right? So we're going to see what will happen if we try to mess with the default cutoff probability. But as a default, we're going to use 0.5. Okay. So this person is going to be what? Not a borrower, right? They likely will not borrow money from the bank. Okay. And I can change that now, right? So for example, what happens if, let's say, instead of 60, there is a customer with 100,000? Are they more likely or less likely? Well, let's see. 100,000. I rerun this formula, and what does it say? 0.08. Is the probability going up or down? It's going up, right? So here's the simple rule, ladies and gentlemen. Okay? The simple rule is that if the slope, this is the slope, right? 0.0371, right? That's the slope from my variable. Okay. If the slope is positive, then increasing the predictor variable results in increase or decrease of the probability. So we have positive slope, right? And we just went from $60,000 to 100. What happened to the probability of 1? It went up, right? So if the slope is positive, what does that do to the probability of 1? Increases that. The predictor goes up, the probability of 1 goes up. Simple rule, ladies and gentlemen, okay? If the slope for the variable is positive, then variable increase results in higher probability of 1. And vice versa is true. The slope is negative, that means higher variable, lower probability of 1. Okay? Positive slope increases the probability, negative slope decreases the probability. Really straightforward rule, okay? Can I memorize that? That should be fine, right? Okay, well, let me show you something else, okay? So let's go back to the drawing board, just like that, okay? So let's discuss seemingly unrelated topic, okay? But you will see in about 15 minutes and 43 seconds that how it's relevant to what we're doing right now. Let's discuss something that's called odds. Odds. You heard about odds before, right? What are the odds of rain today? What are the odds of hitting the jackpot when playing the lottery, right? So odds. Okay. Turns out that odds are related to the probability very closely. So here's the formula. If I have certain event, like for example, let's say I throw the dice, and what are my possible outcomes on the die? Tell me. 1 through 6, right? So probability of each outcome is 1 out of 6, right? I can calculate, so let's say I'm looking for the probability of getting exactly 4, okay? Out of 6 possibilities. It's one choice out of 6 possible choices, right? That's the probability. I can calculate the related odds, okay? So here is the formula for the odds, ladies and gents. If I want to calculate the odds of something, then I have to take the probability of that something divided by 1 minus probability, okay? That's it. So, simply speaking, here is the explanation, okay? In the numerator, I have probability of an event happening, right? Happening. And what do I have in the denominator? Tell me. Probability of event 1 minus p. Not happening, right? So this is probability of an event not happening. Okay, simple as that. All right. So let's have some fun with numbers. As much fun as we can have with statistics, in case you enjoy that kind of stuff, right? Which I guess the majority of people really don't. So if I know the probability of something, then I can easily calculate odds out of that. So let's have some practice. Whoa, look at that. This is some Salvador Dali stuff. Odds. Okay. All right. So, for example, let's say probability of something is 0.2. Okay, that's the likelihood of me getting a B on the next test. Okay, what are the odds of me getting a B on the next test? Okay, so odds, I can easily compute odds like this: P divided by 1 minus P, right? And that's 0.2 divided by what? 1 minus 0.2. 0.8, right? And it's 1 out of 4, right? 1 chance in favor of me getting a B, 4 chances against me, right? That's what it basically means. Okay? So if I have to take the test 5 times, as if I was taking it for the first time each time, right? Then in 1 case, I would get a B, and in 4 cases, I would get something else, right? So I know the probability, I can calculate the odds. Okay, so let's make a mental note. P.2, odds 1 in 4, right? Well, let's move to higher probability, 0.5. Like, for example, flipping a fair coin, right? If I want to get tails, for example, flip a coin, 50-50, right? Okay, so what are the odds of getting tails if the probability of getting tails is 0.5? And the odds are, again, P, 1 minus P, that would be 0.5 divided by what? 0.5, right? 1 minus 0.5 is 0.5, and it's 1 over 1, right? 1 chance in my favor, 1 chance against me, right? Half and half, basically. All right. And the last one, let's do something like that, 0.75. For example, what is the probability of, I don't know, rain today? 75% chance, okay? Well, not today. Today it seems that there is 0 chance, right? But suppose it's like overcast, right, and really dark, so there is a good chance of rain, 75%. What are the odds, okay? So P over 1 minus P, and that would be what? 0.75 divided by 0.25, and that would be 3 over 1, correct? So what do we see? When the probability goes up from 0.2 to 0.5 to 0.75, what happens to the odds? 1 in 4, 1 in 1, 3 in 1, odds go up, right? So here is the rule, ladies and gentlemen, okay? As probability goes up, odds also go up. So essentially, it's kind of an alternative way to think about probabilities, okay? That's it. P goes up, odds go up, and vice versa. Higher odds mean higher probability in favor of certain event, right? Make sense? Should be fairly straightforward. So, that was us converting probabilities into the odds. Can we do it in the reverse order? Can we do it, like, for example, let's say I tell you that odds of a certain event is 4 over 1. Can you calculate from that probability of that event? Well, let's do it together. Let me show you the way, okay? Alright, so odds, again, I'm going to be just writing down the formula. 1 divided by 1 minus P, right? Okay? So how do I unwind something like that? Well, I have to multiply both sides by the denominator, right? That would be 1 minus P. Oops. 1 minus P. So here 1 minus P cancels out. On the left side I have 4 times 1 minus P equals just simply probability. Right? Okay, so here we have 4 minus 4P. How do you call this rule? 4 times 1 minus P is 4 minus 4P. The distributive rule? Should be middle school, right? Yeah, okay. Equals P. Well, I have to bring the 4P to the other side with the other plus sign, right? So 4 equals 4P plus P, or equals 5P. And from here, probability equals 4 over 5 or 0.8, right? So, basically what I'm telling you is this. If I give you a probability, let's say this is the question on the upcoming exam. Wink, wink. If I give you the probability, we'll be able to calculate the odds. Yeah. If I give you the odds, will we be able to find out the probability? Yeah. Okay. They're convertible one into another. Okay. And again, you can ask me, okay, great. Why does that have anything to do with, what is our topic today? Remind me. Logistic regression. And I say, yeah, great that you asked this question. I'm so glad. Let me show you, okay? So here's what our logistic regression looks like. Let me just write the formula like that, what we started. 1 divided by 1 plus e to the power, exponent to the power minus, well, this whole mess I'm going to just call z, okay? And remembering that z is actually what? Mx plus b, right? Slope times the variable plus the intercept, linear portion, okay? Let me go ahead and unwind this expression, okay? So, from here, how do I get rid of stuff in the denominator? Multiply both parts by the stuff in the denominator, right? And oh yeah, by the way, it's not just y, it's actually probability of 1, right? Or I'm going to simply call it p, that's it, okay? Alright, so I multiply both sides, right and left, by 1 plus e to the power minus z. So, it cancels out on the right side, but on the left side it's multiplied by p, right? So I have p times 1 plus e to the power minus z equals 1, right? Because it canceled out from the denominator, right? Okay, cool. So, on the right side I have p plus p times e to the power minus z equals 1. And let me bring p to the other side with minus sign, right? So what I have is p times e to the power minus z equals 1 minus p. Now let me get rid of p. How do I do that? I divide right side and left side by p, right? So p cancels out, and I have e to the power minus z equals p over 1 minus p. Okay? Well, let me flip both sides, right? Because I don't like this minus sign right here, okay? So I take 1 over the right side and 1 over the left side. So therefore, on the left side, I'm going to get e plus z, right? Equals. And in the right side is going to be just 1 minus p over p. I just flip the ratio, right? We're almost done. How do I cancel? John? Oh, right here. Okay. Yeah, well, p, yeah, you're right. I screwed up here, right? Yeah, 1 minus p over p. Yeah, thank you. 1 minus p over p. And therefore, it's going to become p divided by 1 minus p, right? So this is where I messed up. Okay, yep. Great catch. Okay, how do I get rid of e? What's the function that reverses e? Log, natural log, right? So, let me ask you this question. X squared, how do I reverse x squared? Square root, right? X cubed, well, it's a cubic root, right? So, if I have e to the power x, in order to get back x, I have to take natural log, right? Same thing here, okay? I'm going to take natural log of the left side and the natural log of the right side, okay? So natural log will cancel e, right? And on the left side, I'm going to have z equals ln of p over 1 minus p. Well, guess what? What's this portion right here? Let me go back. This is the definition of odds, right? That's why I was telling you this whole story about how we can calculate the odds from the probability, okay? So, on the right side, I have nothing else but natural log of odds, that probability is equal to 1, right? That the customer will get a loan from the bank. Odds of, that's not right, of odds of outcome 1, right? That the customer will agree to a loan. Bank sends him the card, and the customer says, yeah, great, I'm going to apply, okay? Odds of 1. And Z, remember what we called Z? Where is that thing? Oh, God, somewhere here, yeah. So, Z is what we have at the exponentiation, right? And that is big expression that involves slope and the intercept and the whole thing, right? So, therefore, Z is equal to M times X plus B. So in our case, specifically, okay, hold on, I have it written down here, okay? My M was, what was M? 0.03, right? 0.0371 times, what's my X? X is my predictor, which is what? Income, right? Times income. And the slope was negative, B was negative, minus 6.1273 is equal to the natural log of odds of 1. That is just a different way to write the same exact thing, okay? So, this, where is that? Yeah, this function right here, e of 1 equals to 1 over 1 plus e to the power minus da 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 da, is the same thing as what we have right here, okay? Just written a little bit differently, okay? And that actually, again, shows you the same exact rule, okay? What happens if my income slope, this is slope for the income, right? So slope is positive, right? So when the income becomes income plus 1, what happens to the left side? When the slope is positive, it gets bigger. Therefore, the right side should get bigger as well, right? Income goes up, left side gets bigger, right side should get bigger, okay? And here is the function ln. In case you don't remember, it's from Math 135. This is x, this is ln of x. This is what the function looks like. It goes to the point 1, 0, okay? So it's an increasing function, okay? So if my ln is getting bigger, that means that the odds are also getting bigger. So income goes up, slope is positive, left side is increasing, right side is increasing, which means that odds are getting bigger, and we just discussed what happens with odds when they're getting bigger, what happens with probability when the odds of that probability are getting bigger. They're positively related, right? Bigger P means bigger odds, lower P means lower odds, okay? So again, same rule, okay? If the slope is positive, that means that variable goes up, odds are increasing, and the probability of 1 also increasing. If the slope is negative, odds are decreasing with the increase of the variable, right? And the odds are also decreasing, probability goes down, okay? Simple rule. So, remember our discussion, like who are the people who are more likely to get a loan from the bank? Unsolicited loan from the bank, people with higher income or lower income. Well, what do you think? Higher income, right? Because the slope is positive, that means more income, higher the odds, right? Just out of curiosity, what do you think is the cutoff when it's 0.5? What level of income? Hard to say, right? You know what? I think we're out of time today, right? So let's do this. In the next class, I'm going to show you how to plot this function. So we're going to make, actually, let me show you. We're going to make this graph pretty much, okay? And then we're going to see how we can estimate, starting at what income, it becomes higher than 0.5, the probability of a loan. And we start classifying people as ones, right? Not as zeros, okay? All right, this is it for today.